I'll do it at the end. I'll do it at the end. I'll do it at the end.
Okay. Yeah, I'm
Cool.
happy.
Lawrence, how you doing, buddy? How are you?
I'm fine.
Yeah, you good? Good,
Yeah.
good. I should have recorded it at the beginning, and I did a little I shared something about the CV database. Do you know what I mean? So but anyway, I'm gonna hand over to Abdul, and then I'll catch you guys in a bit.
Okay. Thank you. I'm happy to be here once again. Today we're gonna look into what we did last week. We just quickly recap, and then we modify our models to see if we can get a better performance. Last week I said there are so many things we can do to help get a good model. One of the things we can do is to declare another model entirely, different model. Another thing is to work on the model we have by fine-tuning some of the parameters, by so many techniques, using different techniques to ensure we have a better accuracy. So most times accuracy is not the key. There are other things we can look into, and those are what we're gonna check today. So I'll be sharing my Google Colabs, the one we used last week. We just modify some of them today. Oh, please enable my screen sharing. Han? Hello? Can you please enable my screen sharing? Let me quickly contact him so that he can enable my screen sharing.
Sorry. Yeah, no worries. I can do that for you right now.
Okay. Okay, it's enabled now. Please, everyone should confirm you can see my screen. Can you? Can you all see my screen? Okay. In our last class, we looked into some of these libraries, and then we added another libraries like the sklan. The sklan library, we said it can do so many things. Some of the things we can do with sklan is like we can get different models from it. Some of the models, LCV, logistic regression, random forest, K-neighbors, Gaussian, decision tree, and so many other classifiers. We can get them from scikit-learn. Apart from that, there are other things we can benefit from sklan. Another thing we can benefit is that we can split our data into train and then test data using model selection. When we import this, we can use it to split our data. Another thing important of the sklan is that we can measure the models, all these models that we want to declare, we can measure their metrics. Some of the metrics we can measure depending on the type of model we are dealing with, whether it is classification models or regression model. If it is classification model, we can look for things like accuracy, confusion matrix, classification report, ROC, log loss, recall, and etc. Precision. So those are the metrics we can get from sklan. Another thing we can do in sklan, we can do some processing. Some of the processing we can do, we have talked about this processing before, which we call label encoding, that we use mapping for instead when we were doing our preparation, data preparation. We use mapping instead of using label encoding. We have different methods of doing that, one-hot encoding and etc. Apart from that, there are some other processing we can do, like scaling our data. When we scale our data, we mean that we want the data to have a uniform look. For example, you want to scale your data between 0 and 1. You can use normalization, min-max, you can use standardization. Generally, they call this scaling different names. Some call it standardization, some call it normalization, but they are majorly all called scaling. They are all scaling techniques, but majority of people call it standardization and normalization. But whether it's normalization or standard, it is going to be normalization when you use normalizer, and it's going to be standardization when you use standard scalar. But all of them, standard scalar, normalization, min-max, they are all scaling methods. So we use them to scale our data. They have different techniques, different approach to it. But we are not so really bothered ourselves about the approach. Our own is just to be able to import the library and use. So which we are going to do today. Another thing we can do with sklan that is not part of what we have imported, there are some data that are in sklan that we can import directly from sklan without necessarily have to download the data. So for example, things like skin cancer, breast cancer rather. Breast cancer is in the data of sklan, and some other data are in sklan. Apart from that, there are some other processing we can still do apart from normalization, min-max scaling, label encoding, and standardization. We can still do something like dimensional reduction. We can reduce, we can do some things we call dimensional reduction, which I will explain briefly when I get there. Now, we have imported the necessary libraries, and we have treated all the necessary things we are supposed to do in our data, like cleaning the data, adjusting whatever we are supposed to adjust, and we arrived at a clean data that we now use for building our models. Now, that is where we are going to continue today. We were able to build a model last week. I told us there are a lot of models we can employ, and we have used one of the model that can be used for our classification. So that is where we are going to continue. This is exactly what we do when we have a clean data. You see, our clean data, we already have we have our columns. In these columns, one of them is going to be the output, and the other one is going to be the input. The output normally refers to as the target, while the input normally refers to as the features and the targets. Now, we represent our features as X and our target as Y. And we are going to get that from the data we have. And this was how we got that. We just indexed out we indexed out our inputs and output. This was how we got the input in the output Y. We said our Y is the model, is the help model, and the output in the output column is going to be our Y. there is a particular column in our data that is called output, and that is the one we are using as our Y. While every other one we serve as our S, not necessarily everything, but the one we want to choose, we have the balance, day and up to age categories. Those are what we choose as what we are going to use to build our model. After that, we examine what our Y look like after we index it out, and this is what we have as Y. The same thing, we also examine what we have as our S. This is actually what we use as our input in this particular data, in this particular model. This is what we're going to use as our input. So up to age categories. I said we should try, because most of these things we have like job map, marriage map, we have done some engineering on them. I said we should use raw data that contain marriage, job, those that were not modified, and see whether our model is going to perform better. So I don't know if we have tried it. I've not tried it myself, but that is what we can as well try today. So we have both X and Y. Now, after having our X and Y, I added something today. After adding our X and Y, I run correlation on my X, all the features. Because if we have all these as our features, balance day and duration, campaign, there could be cases where some of them there is going to be correlation between some of them. There is a reason for this. You have to check whether some of these input or features, they have some correlation. For example, if I'm running a model that want to talk about the price of a car, and it has something like fuel consumption. Also, it has something like distance covered and things like that. There could be a condition where the distance covered per hour and the fuel consumption is going to correlate. If distance is that covered and the fuel used, if if you travel, okay, maybe the price of a taxi. If I want to build a model to predict the price of a taxi, so it's going to be like if I'm telling you I'm moving from Poole, you'll be taking me from Poole to London. You're going to consider the distance to give me maybe a price and say this is what is going to be the cost. Or you want to look at it like, okay, it depends on the amount of fuel consumption from Poole to London will determine the price. Or you want to say both fuel consumption and the distance is going to be part of the features that I will use to determine the price. I want to believe that in some cases, most of these things, there is going to be correlation between them. For example, the distance and the fuel consumption, there's going to be a correlation between them. And when you talk about the time of the day, there may not necessarily be correlation between the distance and time of the day, whether you are taking in the morning, in the afternoon, or in the evening. There may not be, because the distance is not going to increase. However, there may also be correlation between the time of the day and the fuel consumption, because maybe towards the evening, there will be a lot of hold up, and it may take a longer time and things like that. So I want to see if there are some correlations in my data, and sometimes if there are correlations, if, for example, I have like 5 inputs that are correlated, I might just choose one of them and say, okay, if this correlates with this, correlate with this, correlate with this, instead of using the 05 or 04 in my data, let me just use one of them if there is a correlation between them. And that is why I'm trying to run correlation between the future S, and this is exactly how to run the correlation. You just call for correlation s.correlate. This is just a library, just like you are calling a module. So this is rounding it up to 1 decimal place. So 1 decimal place. So it's just rounding it up to 1 decimal place. And this is just to call on the plots using a matplotlib. So, and this one is calling on the heat map using SNS, Cbond. this is just the description. I think what we are running is like a product subscription. Like if some customer will subscribe to my project, so I decided to call it product subscription, or you can call it anything. This is the title you set by yourself. And after setting it, you are going to get something like this, like in form of this. When you have this, you can see that the first one that says each category is one throughout up to the balance. Okay, it runs diagonally from balance to the age categories. You can see. So it runs like that. We are checking, is there any of these features that contains correlate with each other? I want to believe that if before any features can be said to correlate, whether negative correlation or positive correlation, at least it must have up to 0.5. But as for me, I prefer to say things that are, because anything that is close to 1, we have a good correlation. So if, as for me, I will even prefer something from 0.7, 0.8, 0.9 to assume that they have a very strong correlation. But as it is, if you check, as it is now, it is only 0.7 that seems to be the highest correlation here. Like if you look at this, I have 0.7, another one 0.5, and I think I can see 0.3. 0.3 cannot be said to be cannot be said to be any correlation between them. But if I have 0.5, 0.7, I believe there are some correlation between them. And if I check these two data that are correlated now, if you see P outcome maps, if you check 0.7 up to P days, it means P days and P outcome, they are somehow correlated. And at the same time, P outcome maps and previously, if you go and check the meaning from our data, you will know what they mean, is they are somehow correlated. That is how to check if there is a correlation between our data. Every other one, there is no correlation. You can even see zero correlation. Contact between contact and balance is zero correlation. Between loan and the balance is minus 0.1 correlation. So there is no any strong correlation between my data. Reason why I'm checking for correlation is because if I have data that are highly correlated, I may be forced to go to reason of using dimensionality reduction to reduce the number of features I have. Like now I have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, like about 16 data here. I might want to reduce it to like maybe 12 or 10, even 8, if I see some of them that are highly correlated. So I may have reasons to reduce these data in my models, because the larger the inputs, or the less accurate it's going to be. But if the inputs are less, then the more accurate your model is going to be. So it's going to be preferable that you have lesser features compared to having higher features. So that is the reason why you may need to do some dimensionality reduction. For example, if you have a features like 70 features, that may not be too nice. You may want to reduce the 70 features to like 30 or even 40, or if you like up to 20. But you don't just pick anyhow. You can check the correlation between them manually like this. But apart from checking it like this, there are libraries that can be used for this dimensionality reduction. So that is just by the way. Now, I turn my S and Y into an array, of course, by just calling on those values I have explained. Then I splitted them into S train and Y train. And after that, the first model that we tried to build was okay, let me run this so that my cells will not, I don't know. Let me see if the cells is still active. It's like my cells is no more active. I may have to rerun everything from the beginning. Oh. Well, so checking SRA, turning it to an array is not compulsory. I mentioned it the other time. Instead of using S array, Y array, I could have used S directly and Y directly. So it's good. If I could have said S or Y directly. But I think it's a best practice to use it in an array form. So the next thing we do is to call the model we want to use. And we call it last time, we call it model LR, logistic regression, because we are using logistic regression. You could have called it anything. If you like, you can just say model without telling us the kind of model it is. You can call it anything. So I decided to call it model LR, logistic regression. After running the model, after calling the model, I train the model. Training the model, you use S train and Y train. That you go from splitting your data into S train, Y train, S test, Y test. Then that is where you are going to get the S train and Y train for. So after that, we train. After training, after we call this, we train it. After we train, we predict. After predicting in prediction, we check the accuracy of our prediction. That was where we stopped last week. And we want to continue from where we stopped and build on top of it. But for now, it's like my shell. I have to rerun my shell. Let me see if I still have my data. One thing with Google Colabs, if you leave your Google Colabs on active for some time, okay, yeah, it will disconnect. So I just have to import my data back so that I can start running my shell again. We're using bank full stuff. Okay, let me import it again and rerun the shell so that that's one of the disadvantages of Google Colabs. You don't leave your shell for long. The runtime will be over and then you have to rerun again. Let me run all at once. So everything is running. Okay, now we were able to build our model and we get 0.88. Okay, let's just say 88.90 as our accuracy. If I'm to report this accuracy, I will say the accuracy is 88 points, because this is going to be times 100, and I will have 0.88896. This becomes 90%. So this is going to be the accuracy if we are to check the accuracy of what I've just done now. It means the accuracy is 88.90%. For model, this can be a good model, but you can never conclude if this is going to be a good model. There are ways we can fine-tune this model to get a better one. Maybe perhaps the accuracy is going to increase to like 90, 95, 98, and etc. like that. So there is a way. So the next thing we should be looking into is how can we improve this model? One of the things we can still do is, instead of using this particular model, instead of calling this particular model logistic regression, we could have built another model, maybe decision tree or anything. But even having this logistic regression, there is still a way we can improve this model. But that is just by the way again. Accuracy is not the only thing that we use to check the metrics of our model. We imported some of these metrics. If you check our import, you will see that there are other metrics that we can use, as well as there are other models. We have used logistic regression, talking about the model. There are other models we can use. We can use SPC, we can use logistic regression, random forest, and etc. But apart from accuracy, you see here we have accuracy score. Accuracy is not the only metrics that we can use. We can use classification report, we can use ROC, we can use log loss, and etc. But the best known for majority is the accuracy. We always understand accuracy better than any other one. So, but now I want us to look into other metrics apart from accuracy. We have calculated and we see that our accuracy, we got 88. So what about if you check for other metrics? So how do we check for other metrics? So the other metrics we are going to check, these are the other metrics I want us to look into. I want us to look into accuracy again. I want us to look into recall. I want us to look into F1. I want us to look into report loss, confusion, and precision. So this is the code. I've written the code. If I run it again, it's going to give me all other metrics that we can call on this. You can see the metrics, the accuracy is, this was because I wrote the accuracy is in my print. That was why you are getting that. If not, it's just going to print the accuracy. So the accuracy is 0.88, the precision 0.5, the recall 0.1, the F1 0.2, ROC 0.5, loss, 4, and etc. Report. The report contain precision, recall, F1. You can only call for report in some cases. It's going to give you these 4 parameters already. So without even calling them individually. So you can call for confusion matrix. The confusion matrix says 98565, 137, 1118, and 183. You may not understand what this means, but I will explain. So now these are other metrics that you can call for. The only thing you need to do now is like you have to research on what is the best metrics, what is the best figure you should get for every metric. For example, accuracy, the best thing you are looking for under metrics, you are looking towards 100. But since we are using 0. We are looking towards 1. So if your accuracy is getting towards 1, it means the better it is. So if I get like 88%, 90%, you can see the more the number, the higher the number, the best the model. The same thing with precision. You can see a precision of 0.5. Even the accuracy was 0.88. Doesn't mean that the precision is going to be good. You can see the precision is 0.57, which is not good at all. And this one, recall is 0.14. It's not good enough. It's not good. F1, so some, as it goes down, the best it is. Some, the higher it is, the best it is. But for example, loss, the loss will be going down. So like in the case of loss, like we are having 4 now, if you can get a loss of 0 point something, it means that is a good model. But this one that we are having a loss of up to 4 is not a good one. So the loss will be reducing to 0. So now that it is 4, if I can build a model that the loss will be like about 2, the loss will be about 1, the loss will be about 0.005, 0.5, 0. Like that. So the lower the loss, the better the model. While the higher the order, the better the model. You can see that these are not consistent at all. They are not. This is not a good model that is having a recall precision of 0.5, a recall of 0.1, F1 of 0.2, like that. So this is not a good model. But merely looking at the accuracy, you always want to believe that if the accuracy is like 70-something and above, oh, the model is good. No, it is not always. It is not always. But confusion matrix will now explain it better to us. Now, what the confusion matrix is explaining, you may have a model that is as high as 90-something degree percent rather, but by the time you check the confusion matrix, you just discover that the model is not good at all. For example, this model is having 9865, 137, 1118, 183, which shows that this model is not a good model. How do we know from the confusion matrix? Let's use visualization to visualize our confusion matrix. Let's use it map. So this is what this confusion matrix means. Exactly what you have here. Check the confusion matrix: 9865 137 1118 183. If you check the confusion matrix now, those figures are going to be there. You can see 1118 183. This is what you have in the figure. So what does this mean when we are talking about confusion matrix? You can see that then we have 0 and 1 and 0 and 1. So here I have 0. I'm trying to see how I can make my screen bigger, but I don't know. I want to believe you can see the screen at your side. I want to believe you can see the screen better at your side. Everyone? Okay. Okay. Now, you please look at this confusion matrix very well. It's very important when you are doing classification. It's very, very important. So apart from, if you just look at confusion matrix here, you just look at it like when you check before we do the visualization, it doesn't really make sense. The confusion matrix is 9865 137 1118 183. It's just like a matrix, 2 by 2 matrix. So, but by the time you plot it, it makes better sense. Now, what this implies is that you can see here we have 0 and 1, and under here also we also have 0 and 1. I want to transpose that to upper part and say this is 0 and 1. So in this first contrast, this is 0, 0. It means if we assume that at this part your y-axis is if you assume your y-axis to be actual, if you know we are predicting, we say actual class and then predicted class. So if we assume that this place, this 0 and 1, they are the actual class, and the other 0 and 1, they are the predicted class. Here, predicted class. Why this is actual, assuming we label it as x-axis and y-axis. So the x-axis is going to be, the y-axis is going to be the actual class, while the x-axis is going to be a predicted class. This is the implication. If the actual class say is 0, that is when we are predicting, you can discover, you recall that what we are predicting, we were trying to predict S. And when you go and check under our S, is primarily 0 and 1. You go and check our heads. Let's check our data again. What we were predicting is this outcome. And under the outcome, all what we have is 0 and 1. Like true and false, depending on what we are predicting. That is exactly what the confusion matrix is showing us. That the actual prediction is this 0 and 1 that we are predicting. When it was 0, the model was able to predict this is 0 and 1 as well. So when it was 0, the model was able to predict 0. So it means we have true we have what we call true negative and true positive. Yeah, true negative and true positive. So let's just assume that 0 is negative, right? Why 1 is positive? This one is going to be true negative. We were able to predict a true negative of 9. Why it was true was because this was 0 predicted. Let's check the labeling down, because okay, this is the labeling 0 and 1. So anything that is in the first row here is 0 and 1. So just like the way we check our 4-figure table and our timetable, this is 0 and this is 1. Here we say 0, 0. So when it was 0, it was able to predict 0 of this. And when it was 1, it was predicting 0. When it was 0, it was predicting a 1 of this. Which shows that this one was wrongly predicted. Because if this is 0 and this is 0, and it was able to predict this as much as 0, it means it was able to predict good number of 0. But at a point, it was classifying some of the 0 as 1, because this is going to be 0, while this is also going to be 1 for the prediction. So this is 0 prediction and this 0 actual. This is 1 prediction and this is 0 actual. So which shows that 137 was predicted wrongly as being 1 when it was 0. But 9,865 was predicted rightly as being 0 when it was actually 0. I hope you're getting that now. But when you come to this second part, it was 1 here, predicting 1 when it was supposed to be 0, which shows that this was predicted wrongly. While this was predicted rightly, 0 and it was supposed to be 0. This was 1 and it was supposed to be 0. You can see that the classification was wrong. Now, by the time you check the down one, this was actual 1, right? But this was predicting it as 0. Predicted as 0 when it was supposed to be 1. But this one was 1. This one was 1. So it predicted this as 1 when it was supposed to be 1, which was correct. We saw that this was wrongly predicted, which was much. This is not a good one at all. What we should be expecting at this opposite side here and here should be a very low number. Say, for example, like 10 and say like 2, 8 here. You understand? Which shows that maybe 8 was predicted wrongly, and here maybe like 1 was predicted wrongly, which is going to be good for the model. But look at the number of 0 that was predicted when it was supposed to be 1. And look at the number of 1 that was predicted when it was supposed to be 1. This was correct. But it was able to predict 0 very well, because this was supposed to be 0 and it predicted it as 0. And this was supposed to be 0 and it predicted it as 1. So we have the true positive and false positive. We have the true negative and false negative. But the most important you should be checking in your confusion matrix is that this opposite side, they are supposed to be small. Let me share. I have some of my models that I've used before, I've built before. Let me stop this and share another model. Another of my work that is not this. I was working on a different model before. Let me share. Can you see this? Okay. Can you see what I'm sharing now?
No.
Okay. Let me check again. I want to share some of the work I've done before. I actually want you to understand what this means. Can you see this one? Can you see my screen now?
Yes.
Yeah, this is my Visual Studio. Okay, yeah. This is a work I've done on breast cancer before. Okay. You can see some of them. There are some of them that correlate very well. You can see the correlation, they're having 1, some of them 0.9. You see this correlation, the correlation are high, but that is not even what I'm trying to. Hey, look at this. Look at this model. It was predicting 3 wrongly and was predicting 2 wrongly. You can see that this is good. It's not this opposite side. You should always get a low number here. 85 was predicted correctly and 53 was predicted correctly. But 3 was predicted wrongly and 2 was predicted wrongly here. You understand? Which was okay. And if you check out that model, I tried to do another thing on it to see if the model can increase. And you can see it was still the same. It wasn't increasing. I still do some other thing. You can see now it was only 1 that was predicted wrongly here. Why this one was predicted wrongly? I think this model performed better. And if you check the recall for this, you can see the recall is 0.9. You can see 98%. And the precision 98%, the recall 94%, and then F1 95, 96%. You can see the higher all these things are, the better your model is gonna be. You can even see that the precision was 98 while the accuracy was 97. You can see it is the precision and the recall that matters to me here, not even the accuracy. I can have the same thing that have the same accuracy. You can say, okay, the accuracy is still 96 here, okay, wow, it's lesser, okay. So they may have the same accuracy, but the recall and the precision may be higher. I will prefer the one that have a higher precision and recall because it's going to make my confusion matrix to have a lesser miscalculation, misclassification rather. You can see this is a better model here. Okay. If I have a model that we only make one mistake or maybe 3 mistakes out of like it is something, is good. It's good. The percentage of the mistake is less, so it's going to be a good model. So I'm just showing you this. Let me go back to what I was sharing. So you can build a model that will perform very well. You have to just continue to fine-tune so many things. You can see this one this 1118 that was wrong. I could have done another thing that will make it better. I could do some other things that will make it better. So those are the things we are looking into. How do we make our model perform better? Not only in the name of accuracy, in the name of, we can see the precision. See this precision that is 0.14, something that we are expecting that should be around 100. This one that we are expecting to be around 100 is 57. You can see the model is not good. Accuracy alone does not actually, if you build a model and you have an accuracy of 90%, don't think the model is good. Check other, what do you call it? Check other metrics. Check other metrics. And the lower this one, the loss is, the better the model is still going to be. So these are other models we can check for our other metrics that you can check for our model. This is not a good one. See the number that was calculated, 1118 and 137. If there is a way we can reduce this thing, it means the model will be better. Let's look into a way we can reduce that. But before looking into a way to reduce that, looking into a way to reduce that, things we can do. Number one, we can look into another model, declare another model. Instead of using logistic regression that we declare here, we could use another model and see if the model will perform better. The fact that the logistic regression is not performing well on this data doesn't mean logistic regression is not good. It depends on the data. Sometimes logistic regression may be the best for the data you are using because of the different relationship that exists in this in the data. So the fact that you have a poor accuracy from your logistic regression and get maybe a good one on another one doesn't mean that one is better than logistic regression. If you go and get another data and you do that again and you were thinking that that one will perform better than logistic regression, you may be wrong. So you just have to try different models to see the one that will be good on that particular data, because models they are data specific. Yeah. I have a publication where I was able to justify that there is no model that is better than one another. One model is not better than the other. What determines why a model is better than one another is the nature of the data you have. That is what determines which model will perform best. So now one thing we can do is to choose another models and look at the other model we want to build here. Now we have established we have different models in our SKLN. This is some of the model we have. We have KN classifier, we have SCV, we have decision tree, we have Gaussian, we have random forest classification, and etc. We have lots of models. So we want to try some of this model, and if I run this, let's try one of them. I declare all of them at the same time because I just want to be picking you, but I use different names for them so that I will know the one I want to refer to at a particular time. Now, I want to refer to the first one. I call it model. Okay, I want to train this model and predict at the same time. I choose the first model I declare. So this one was the one I choose now. So I picked the model. Of course, you know the procedure. After you declare your model, the next thing you do, you fit it. After you fit it, the next thing you do, you predict it. It's the same format that you follow every time. So now the next thing is for me to fit it and predict at the same time. So I fit and predict. Is training the model already. After training, I'm doing it on the same shell. It's going to train and predict at the same time. So it has trained it and it has predict already. So after training and predict, let's check other metrics, all the metrics. I decided to name this one Y predict K, referring to this model as K, because if I just call it Y predict, if for any reason I didn't run this model in this shell, I've forgotten and I didn't run it, and I run this, it's still going to run because I already have Y predict. It's just going to pick the former Y predict. So you have to be very careful when you have a lot of model in a single Jupyter notebook. Normally, I'm supposed to build different Jupyter notebook for them, so I wouldn't bother whether to be renaming anything. But now, since I'm building everything in the same Jupyter notebook, I have to be very careful and renaming it so that I will not be running another thing thinking I'm working on a particular model. So that is why I just decided to use K to differentiate it from the first one that I predict. So now that I'm using K to differentiate it, it's the same K that I will be using, because now I already have Y predict, but now I'm not using the former Y predict, I want to use Y predict K. But Y test still remain the same Y test, S test still remain, and train, everything still remain the same thing. The only thing that has changed now is the Y predict. The model has also changed at the same time. So the model has changed, the Y predict now has now changed. So I have to indicate so that I will not be running the former one. It's still going to run if I don't put it, but I will be getting the answers, results for the former one, and I will be thinking is this one. So that is why I just have to be careful and put some things to differentiate them. It's just a naming that I choose. Okay, what went wrong here? Incomplete input. Okay. Yeah, I didn't clear everything. I was clearing what I used to comment it before. Okay, should be complete now. Okay, now I've run this model, and this model is known as, okay, it's still 88. It's 88, 0.57. Nothing has improved. 0.1 is almost the same. I don't think anything has improved here. So let me run the confusion matrix for that. I'll see. Nothing great has actually changed in this model as well. Oh, is this one performing better than the former one? I'm not sure. So by the time you check, you see if it is performing better or not performing. So you choose another model again. That is one of the things you can do. Okay, let's try this and see. Let's try this model, which we call let me just copy this and replace. Okay, okay, let me create it up here. Let me run another model. Let me just create a space here. Let me copy all these. But the only thing I will change now is that I will change the name of the model. Let me change it to this name. This is the model I want to use. Let me just, you have to be careful. Okay, I've changed it. And let me change this one to S now. S, so that it's going to be different. So I've run that and I'm predicting that. So it's running and predicting at the same time, but before it's done, let me copy the metrics again. Let me just copy the old metrics. I want to run the old metrics for that one at the same time. So while it's running, let me keep modifying the metrics. I'm just looking for a model that will perform better. So one of the things I can change here is that this K, I can be changing this to S. One thing is that the time taking for different model to train differs. Why some might use some seconds, some might use some minutes to train. So let me just change all the K to S here to differentiate it. Okay, and let me turn all this one to S as well, so that it can be differentiated from. It's still running. I don't know why it's taking longer time for this particular model. some model takes longer time to run. So, but sometimes even if they take longer time, they may perform well. One of the things you are careful about is the model time. Some may take a longer time before it can actually train. Some will take some. So you will want to choose the model that will not take longer time in some cases. So this one is taking a longer time to train. So if I've known, I wouldn't have taken that. I would have taken another model that is easy to train, because we have the data is somehow much a bit, so it may take some time for this SVC to train the model. So it's training the model and it's taking time. So we cannot do any other thing other than to wait for it. But if it can take a longer time and give us a better result, then it's better. It will be better if it can take a longer time and still give us a better result. So, but one of the model I love to use is this GND. I love it so much. It normally gives, most times, it normally gives a better result. It normally gives a better result. As I said earlier, there are other things you can do to improve your model. If after I run this model and I discover that the model performs somehow, and I'm thinking of changing, maybe it's still the same model, I can still run the same model, but just change some parameters in it. Like this kernel now, there are other values you can use instead of using linear. You can use poly. You can use poly like these. These are numbers. You can change the number here. So depending, you can keep changing and see whether if you use a particular number, your model will perform better. Or when you change the kernel, you can change, I think you can change up to like 4 different kernels for this. Instead of using linear, I may decided to use another one. So if I use another one, I may get a model that will perform better. Like the first one I use, KMC that I use. If I change this neighbor to 5, it may perform better. If I change this to 10, it may perform better. If I change it to 4. So you can check a range of value from maybe from 2, 3, 4, 5, 6, 7, 8, 9, 10, and see the one that perform best and use that and neighbors. So those are some of the ways you can also use to fine-tune your model. So like this one that I'm saying maximum depth is equal to 5. If you like, you can change it. You can change it to like 10. You can change it to like 4. You can just check random number between 1 to 10 and see if as you are changing it to 5, it performs better. You change it to 6, you get a better result. You change it to 7, the result is not as good as 6. Then you go and check, try 4 and see. And then if you get a better one, you stick to that for that particular data. And then that means you have changed some parameters to get a better result instead of changing the models. Another thing, I don't know if this is taking time, I may just have to abort it. Let me abort it. If I can abort, let me see if that can be aborted. It's taking longer time. So when you have a time, how can I abort in this situation? Yes. Yeah, okay. Since I've aborted it, let me see. Yeah, let me change it. Let me use this. But I may not bother to change any other thing apart from just changing the model name. So I may not bother to change S to GND. Let me just run it that way. Oh, what happened? Oh, it means I have to run from the beginning again. Oh, so let me run again. I think since I aborted it, I have to, let me check if my data is still running. Oh, I'm not sure my data is still there. It's taking longer time. Bank. Oh, And let me rerun everything again. It's not going to take time, provided the shell is active. Okay. So now let me rerun again so that let me see my runtime. I can't find my runtime. Oh, I'm looking for the runtime. Okay, I've seen it. So I want to run all at once so that it won't waste our time. Running each one after the other is not going to be the best for me. Okay, so I think I've gotten here. Let me see what happened here. Let me run this. It's running, but what happened? It can't find this model. Okay, maybe I didn't import it from the beginning, but if I didn't import it, it's not supposed to, let's check. If you imported, it was imported. This is it. It was imported. So what actually happened? And we have declared it. Oh, yeah, I've seen this model. I didn't change it here. Yeah, this one, you can see the problem. I didn't change the model here. I didn't change it, okay? So, okay, that's run. So let's check the performance of that and see how good this is gonna be. Oh, I didn't change. What happened again? Accuracy K. Let me see. Accuracy. It was not supposed to be running accuracy K. Okay, yeah. I've changed everything to S. That is the problem. And the reason why I was getting that was because I didn't run K before. If not, I would be deceived. I would be thinking I was getting something, but it's going to be giving me, you see, I didn't change this. That is why sometimes I would prefer you just do a model per notebook. Okay, I've run this, and this is what I'm getting now. Oh, 85. I think this one performed better now. But the loss is high. 5 is higher. So I'm not seeing anything better here yet. But let's check the matrix. The matrix is not good as well because we have this here and this at the other side. Says, oh, I think this look better. I think this, oh, this cannot classify this other one, but let's see. Let's draw it. Let's plot it. Let me just copy and plot. So this is exactly how we'll be changing everything and be checking if we have performed anything better. But remember, the confusion matrix I'm using here is S and not K. So let's see the confusion matrix for S. Oh, this is not good. You can see this is not good. See, this is very much, and this one again, 633, and this is 1046. If we compare it with the other one, is it better? I can't say yes. So that is on this. It's not a good one for me. I am not saying this as good at all. So let's run this to compare. I'm trying to compare the confusion matrix for the 2 and almost for 3 now. Okay, this one is 1046633. Oh, 137, 1118. I'm checking the wrongly calculated 633 and 1046. This one says 1118 and 139. Yet they are not good. They are not a good model for me. So anyway, that is how you are going to continue doing everything. I'm fixing another one. Check the accuracy again for K. I don't want to when you get to your, when you have your time, you try as many as you could. You can see I'm trying different models. So when you get home, try different models on your own. Now, if I stop at this model, apart from choosing different model, what other thing can I do? I can do what is called scaling. I can scale my data, because if you check this data, you will see some, for example, this duration. Some duration is 365, in 361, some is 92, some is 457. You can see some is 977. You can see that the data, they are not within the same range. The things that will be within 0 and 1 will be in the same range. Check the balance. Look at someone having 2,000 and someone is having just only 1. You can see they are not within the same range. So what we can do is that we can subject all this to what is called scaling. We can scale our data. And I've discussed different kind of scaling with us. I said, if we are scaling, we import some of these processing libraries that can help us to scale. We can use a normalizer, you can use a min-max, and we can also use standard scaler. Label encoding is not for scaling. It's just for something like the way we are putting what do you call it? Like encoding, yeah. The way we are just encoding some of our data using mapping. So that is what the label encoding is used for. But now we want to use scaling, and the scaling we want to use, we have like about 3 scaling we are going to use. Let's use them one after the other and see if there's going to be a different outcome. But one thing I want to make clear here is that scaling is not an automatic evidence that there is going to be a positive change. There are sometimes you use scaling and it's going to even go worse. There are sometimes you use scaling and it will perform better. So it's not a guarantee that your model will perform better. But that is one of the ways. You can see changing your model is not a guarantee that your model is going to perform better. So you change your model to another one, you may be lucky you get a good model that will give a better result. So, but now, talking about scaling, one of the ways to scale is to call on the libraries. And these are the libraries we are going to use. We have called on them already. We have imported them initially. So the first thing, different scaling techniques is what we are going to use here. One of the scaling techniques we can use is min-max, which we already know. This is a min-max scaling technique. Let me just put it. Min-max. This is a min-max scaling technique, and this is how to call for it. So you call for the min-max, and the range min-max, I want it to range between 0 and 1. Any data in our data frame should be should be modified to work to be within 0 and 1. That is what this is going to do on it. And after that, we are going to change our train data sets to fit into this min mass. So it will automatically work on it using our train data set and test data set. Your S test and your S train, you are not going to do that on Y, because Y is what we are looking for. You don't need to scale any Y. Y is either 0 or 1. But we are going to, the inputs are going to be modified. So that is in this main mass. And this is how to call for, if it is only min mass we are using, this is how we are just going to approach that. And then instead of just using our S test, anywhere we are using S train and S test, we are no more going to be using S train and S test. We have changed this to another name, S train min mass and S test min mass. Reason is because we use min mass on it. We can still leave it at S train and S test. We can still say S train is equals to, but it's better we name it that way, since we already aim to use different type of what do you call it, scaling techniques. Because I just say S train and I still call it, when I come here again, I still say S train. So at the end, when I'm calling it, the system may not know the one I'm referring to. That is why I have to name it differently. So if I'm not using that, I could as well use using normalization. I could as well use normalization, and this is how to call for your normalization. There are actually different type of two different type of normalization. You can use what is called L1 normalization, when you say num is equals to L1, and when you say num is equals to L2. They are different approach. They are two different approach. I don't know what is wrong with my Google Colab. Everything is just going off. My connect again. I have to be connecting every time. I don't know. So if I run now, we have to run again. But anyway, let me just explain. So I may use normalization using L1, normalization with L1. And you also have normalization with L2. They are two different approach, but they are both normalization. So you call them the same way, but you specify norm as L2, not capital L. When you are, I'm just putting capital L so that you can see that it was L. So if you are not using that, you can use standardization. So you use any one of them, like standardization. Okay, so if you call it this way, you are using standardization. So I'm not sure if my spelling is correct. Yes, it's not correct. Try to correct it. So this is how to call for it. The same way, the only thing we are only changing our S train and Y train to the name. I call it scalar. If I like, I can call it standard. S train standard. Y train, S train standard, and S test standard. So we saw that anywhere I want to be building a model now, I will not be just be saying S train and Y train, and S train and S test. I will change the name to whatsoever of the standardization I want to, whatsoever scaling I want to use. Let's use the first scaling, techniques. So the first scaling techniques I want to use now, I want to use min mass. If I'm using min mass, what I want to do is that at the same time, I want to build a new model using the first model that we built. You remember that first model was logistic regression. It was still the same model I was calling for. Model logistic regression.fit. It's going to override the former fit, because this fit now is not just using S train, it's using S train min mass. This one is using S train min mass that I declared under min mass, and it's going to use S test min mass, since I want to use min mass. If I'm not using that, assuming I'm using this, I will be using S train L1, S test L1. So but since I'm using min mass for now, everything will change to min mass. So I've changed everything to min mass, and I want to work on the metrics. I put everything in the same shell. If I run this may not run because my my cell is already dead. Let me see. Oh, it's not. I have to run again. I don't know why. Maybe it's network. The problem with Google Colors is that when your network has a problem, it will always, you know, since we have been using it, we have not been calling this every time like this. I have to always put this every time now because I think it's the network. So I have to always input this and run again. Your own may not be like that, so you don't have to bother. It's because of the network at my site here. So I have to rerun again. Oh, I hate this. Okay, let me rerun again. Runtime, run on. Let me just wait here. It's going to be fast. This is what I'm waiting for. So let's see if before then, let's quickly see what we have initially under when we run. Let's just master it and see if there will be. Here we were trying to run logistic regression without any scaling. And when we run the logistic regression without any scaling, the output the outcome, the result was 0.88, 0.5, 0.14, 0.22, 0.5, and 4. You can see the loss was 4 here. The accuracy was 88. The precision was 87, and this one we have 14, and this one we have 22, this one we have 56. So let's check if after we run, please just, okay, let me just copy it so that we not have to be coming up. Let me just copy the result and so that we can easily compare. So, and of course, oh, I would have loved to also compare this. So let's go to where we have it. After running this, now this is what we got. Yes. This is where we run min mass. Yeah. So let me put, this is the result we got. Let's compare it with the result of, let me just create another and paste the result here. This is the former result. Let's compare. We have 88 and here we have 90. Yes, let's compare. Let's compare them. Let me copy this and put them side by side and let's see. Can't put it side by side, but okay. Let me just put it up so that it can be easily assessed. So we have 90. This one is 90. This one is 88, which shows that there is an improvement. This one is 57. This one is 67. Oh, almost like plus 10. This one is 18. You can see this one is not still good because we are only having 28. And this one is 14, right? So not still good. Now the F1 0.22, it has improved to 0.4. It has improved to 40% from 22%. And this one has improved to 56. No improvement. This is 63. This is 56. Anyway, okay. Oh, it has improved to 63 from 56. So there's an improvement. And this one, the loss is 4. Okay, it has improved to 3.5 from 4. So we are looking towards making this loss to be equal to something close to 0. So and something that was 4 before has actually improved to 3.5. So you can see there is an improvement in the scaled. But that doesn't mean if I use another scale technique that is going to be a good improvement. I'm not sure of that. So let's see what let's see what this one have to give us. The matrix. So let's see. This one, yeah, I think there is an improvement here. This one is 928 now. Why this one is now 82? Let's see. This one has improved to 372 in 373 from let's check what we had initially. 373 from 183. It has improved to 373. Where we need an improvement is these two. We want this to increase, this one, and we want these two to reduce, this and this. This one is 137, and this one is 1118. We want them to reduce. 1118, we want it to reduce from 1118. Let's see what we now have. It has reduced to 928. It's still not good enough. I'm looking for a time I will be able to see it reduce to like 50. That is going to be the best for me. If I can reduce it to like 5, 10, that is what I'm looking forward to see. So, and it's good there is an improvement when I use min mass. If I don't use min mass and I change it to another thing, there may be no improvement. So sometimes min mass may perform best, while the other one will not be good at all. Sometimes normalization may perform best, L1 may perform best, while L2 will not be good. Sometimes L2 will be good, while sometimes standardization may be good, while min mass and others may not be good. So that is how we check them one after the other and check the one that is good, that is better. But for now, this is better. From this has increased to 67. But it's still not still good. I am looking for a case where I will have this 67 to grow to 90, and this record to grow to 90, this F1 to grow to 90 or 80, and this one to grow to like 80, 90, and this one to reduce to 0 point something. So those are what I'm aiming to get. And one other thing I can begin to do now is that you may just begin to change so many parameters and things like that till you are able to get one of the best methods you can use. Apart from that, there is a way you can quickly get a prediction, something that will just predict for you and give you an idea of the best model that you can use. You will now take the model and now begin to do so many things on the model. One of that one is called lazy prediction. So you will install lazy predict. So once you install it, you import it. So from lazy prediction, you can import this one. Let's see. So if my shell is not going to die again, let's see. So if I import a lazy, it's trying to import different type. That here we say lazy prediction dot supervise because we are doing a supervision. Supervise and what do you call it? Model. You know, I said we have supervised model, unsupervised model, okay, but we are majorly working on supervised model. And I also said we have classification model and a regression model. But since this one is classification model, that is why we are using a lazy classifier. I told you that there are some models that are meant for classification and there are some models that are meant for regression. Regression, they are things like that predict continuous values like price of the of a flat or something like that. So if you are trying to build something that we be talking about price, you are not going to be using classification. You are going to be using regression. So in that case, you are not going to import lazy regression. You are going to you are not going to import lazy classifier. You are going to import lazy regression. So, but since we are in classifier, that is why we imported this. Now, if I run, I'm saying, okay, check every classifier model that you have, because this lazy model already have a lot of classification. I think up to like 28 different models in it. So if I run, let me run. I'm still running it on the train test. I'm not running it on any modified test. I'm just running it normally. That is why I just say S train, S test, Y train, Y test. Assuming I want to run it on the min mass, I just say S train min mass, S test min mass. There's no Y train, and there's no min mass for the Y anyway. So, but I want to run it without even taking anything into consideration first. So if I run, I hope my shell didn't die. If my shell, because this will be running up to like 20. Okay, now you can see it is giving me about 29 different models. So we quickly just randomly check 29 different models and give me an idea, a model that will run best that I can concentrate on. I will now, after I run it, I will have an idea of the model that I should fine-tune. So I can just pick the model and start building on it. So this is going to give me an idea of the model that will be the best for this particular data. Oh, I'm at 28%. 11 out of 29 models have been declared. I just hope my shell doesn't die. So, because sometimes when I try to run it, it dies at about 40%. Dies at about 40%. So I don't know why. So it may not be like that at your own side. And sometimes it depends on the memory, the model of your system, your network, and so many things contributes to that. Sometimes it depends. You know, we are using Google Colab. Google Colab also have a paid version that we have a lot of things we can do. Build another faster model and things like that. So since we are just using on paid version, there are things that we go slow with it. So let's just hope it will get up to 100%. So this lazy model will give us an idea of the model. Oh, 41 already. If it can get up to like 50, I'll be sure my model will be fine. Because it's my share normally die when it gets to about this 30 something to 41%. But once it goes beyond this, then it means the shell is not going to die. Let's see. Oh. It's going to give me a runtime. So those are the things we can do. And the other time I was mentioning dimensionality reduction. That is another thing we can do and say, okay, model, help me to check some of the features that are good prediction, that will be good for my prediction. Use those models that will be good for my prediction only. In that case, you will call, oh, you can say, that is exactly, it has crashed. It has crashed. That is exactly my problem. Let me try and run again. That is the problem for me now. Oh. I don't want this. Bank. When it crashes like that, then I have to start from the beginning again. But I will use, let's see. Okay, let me try again. Let me run from the beginning again and wait here for it. The runtime, it may not, all this thing that is happening may not happen. It's talking about the RAM. I don't know why. Maybe the machine RAM, definitely it's not my system RAM. It's going to be the RAM allocated by the Google Colab. The RAM for the system is quite good. So, of course, if you are running a paid version of the Google Colab, you can buy extra RAM. So since this is not using my system RAM, it's using the Google Colab, so that is just the major problem. Okay, let me see. If you want to be, sometimes you have to be paying for some stuff if you want to be using things like this. For example, if I want to be doing an image classification on my Google Colab, I will definitely have to pay, run a paid version of the Google Colab so that I will not be encountering a problem and it can run faster at the same time. So all this I'm doing, I just want to run it and get an idea. It's like it's scanning through different models. Okay, let me check this, let me check. And when you check everything, say out of these 29 models, check them. You will see some that have a good accuracy. Pick them and work on them. That is what it's just doing. So that is what the lazy prediction does. It just help you and it will summarize everything for you, their percentage accuracy. So from the percentage accuracy, you say, okay, this will not work best on this data. Okay, let me go for this. Then you now start afresh and build that from scratch. You are not going to rely on the one given to you by lazy prediction. So it's just a way to quickly get things done. But if it is just for demonstration to tell you that we have model that can build different accuracy, then you can use it to demonstrate. But if you actually want to build, you have to just pick it, do it, and pick and start from scratch to build that particular model, not working on the one given to you by lazy prediction. So let's see. If it doesn't work this time around, then you just go, okay, it's like I have another version that I've run before. Let me just copy, while it's running, let me look for that and run that. And click on that, share it with VS Code instead of using this, so that you see what I mean. I already have it saved. I have saved it. Oh, it's not working. Oh, the save version is not the one. Wow, it was the wrong one I saved. Okay. It's not a problem. If you can't get it, then when you get home, you can try it yourself and see at 41. If it can go beyond this 41, it means it's not going to crash. I should have saved it when I got the opportunity the other time. Okay, now another thing, let's see whether it's not going to crash. So if it doesn't crash, good. So another thing I want us to do is like, you see all these things we use for our eggs. And our eggs, I'm looking for a case where, oh, it wasn't working. So I'm not going to stress myself again. So when you can try it yourself and see whether it works for you, since it's not working for me. So now another thing I want us to try, we modify some of these things like job mapped, married mapped, education mapped, default mapped, housing mapped, loan mapped, all these map. Let's see if we can work on models that we will not use. We are not going to use all those map. We just use it directly and see if we are going to get a better output. Sometimes we get a better output even at that. So, and I already said we should do that. So I don't know if anyone has tried this. So let's see. But the problem now is that I have to rerun my shell every time. This is actually something I'm not happy with today. I don't know if it is network. I'm not happy with this today. Let me just comment all this out. Now, for me to run again, I have to import my bank. Okay, while I'm running Hull, let's let's quickly build another model that will not require Let me just, okay. Oh, it's still running. I'm still tempted to want to try this once more. I'm not happy with the way this model is not running. Oh, it's like it has run. Good. Oh, okay, maybe. Oh, no, not. I think it's at the point of, oh. Let's see. I still don't want to give up. It's taking our time though. Hello, everyone. Please, you can ask a question. Why this keep running? Ask any question from what we have done so far. Unmute yourself and ask questions. Hello, everyone.
Yes.
Yeah. Please ask your
So,
question.
so after using the model to do the prediction,
What do you say?
what after using the model to do the prediction, are you hearing me?
Yeah, I can hear you now.
Yes, after doing the prediction,
Yeah.
what is the next step? Is the information passed on to like a data analyst?
Yeah, the only thing you do now, after we have built the model and you see that the model is good, you must be sure that the model is good. Once the model is good and you have checked everything is performing well the way you want, the next thing is that the model can be deployed. So people that are into deployment, they already know what you mean when you say you deploy a model. It can be put on use rather. So the only thing that will now be done is that you will now look for someone that have maybe you now use this for someone. For example, you check someone, you can use me for example, check my balance, check, maybe try to call the last time you called me or the number of times you called me, then check the duration of time you used to call me, you have been recorded, then the number of campaigns you have done to me, the P-day, everything, you will do everything with me. Of course, you will going to know my job category based on the job categories we have. You're going to know whether I'm married, you're going to know the education level, you're going to know the defaults, whether I'm defaulted or not, you're going to know this, the housing loan, you're going to get all the details from me. The only thing you are not going to know from me is whether I subscribe to it or not, whether I will subscribe or not. But once you are able to get all these things, you can now use the model on that. So once you put it into the model will tell you whether I will subscribe or not. So the model will only output 0 or 1. That is the last thing. It can even be in form of app. It can be integrated into a app. It can be integrated into a web browser or whatsoever. And say, okay, put this. When you put all the data, it will definitely tell you whether I will subscribe or not. The best way to understand if it is an image classification, you will understand that better. For example, I built a model from image that can classify an image into dog or cat. So I will have and maybe I have a image that have lot of cats and dog, maybe like 1,000 cats, 1,000 dogs that I used to train the data. And the data has performed very well in the model in which I used to train my model. And the data in the models have performed very well. I am sure that the model is very great. Now, it can now be put into deployment. When it is put into deployment, all you just need is to just bring an image of a cat and use it on the model. The model will just tell you this is a cat. Or you use it, but now you know what we are building is telling us 0 and 1. You understand? So when you say 1, it actually means what 1 is, whether subscribe. When you say 0, it actually means that telling me that, oh, this is telling me that this will not subscribe. So for the image, it's easier for people to understand. When you say card, it's definitely telling you that the image you now put, you are going to import the image and use it on the model. There is a way you will build the you are going to call on the model and say, model, see a particular data here that is different from the data you are used to. Tell me what is going to be the outcome. It's just going to tell me that, okay, since the outcome is classification, the model we are building, the outcome is, you can see from the matrix that the outcome is either 0 or 1. So the model will only tell you it is 1, or the model tell you it's 0. So that is the last thing of every job you are doing. So now we have been able to use it to predict. But now, before you can predict, all the features that you use to build the models must be present. I hope you get the point. For
Yes,
example,
understand.
I want to predict the price of a building. And the features that I use, they are the length of the building, the width of the building, the height of the building, the location of the building, maybe what else can I use? Maybe whether it has a compound or not, whether it has a parking space or things like that, the number of room in the building. Those are things I use to predict and to build my model. And I have lots of data for this. After I build the model, now the only thing that is necessary for anyone that wants to use the model to do now is just to bring all this data and say, okay, I have a building in London. Okay, this building, of course, I already get the location that the building is in London. I already get it. Okay, it has this number of rooms. It has this number of toilet. It has this, this is the location. This is this. This is that. Okay, please, what is going to be the price? So since I already built a model that's work and that has all these features, I just call on the model and say, okay, model, see these features, what is going to be the likely price? Then if you just bring it out and say, okay, with these features, this is going to be the price. And that is your work stop at when you build the model. The only thing you just need to do is, how do we now test the model? That is the only thing that is left. We just build the model, we save the model somewhere, and when you save the model, there is a way we test for the model. Okay, so maybe if I'm able to use, it's difficult to use this kind of data to explain. Okay, another one of the greatest one that is easier for people to understand is road sign and pictures. Okay, the road sign. So for example, when you build a model that use different road sign, when you have zebra, when you have this, when you have that, when you understand, when you have maybe speed limits and stuff like that. So if you build it with different, like you have like maybe 30 different signs that you use to build the model. Now, you now bring a particular sign to the model and say, what signs is this? It's definitely going to tell you that this signs represent this. That is exactly, when you build the model, the only thing you do is to store the model, to save the model. And when you save the model, you can always call on the model. Just call on it. It's going to tell you what you are predicting. It's going to tell you. It may not be able to predict everything. It may not be able to predict correctly every time. Maybe, for example, you are building a disease for cancerous disease, and you already have the X-ray. You have an X-ray of the chest, and maybe a chest X-ray that is used, and you use it and say, okay, please predict this for me. And you say someone has a COVID-19. Because of what has been built on, if you put another one and say it's not having COVID-19, it's not 100% going to be correct in most cases, depending on, that is why you have to check if your accuracy is high, if your precision is high, if your recall is high. You have to check all those stuff. Or head is going to, and this is the reason why your this thing is very, imagine something that is already telling giving us false classification here. Something that is supposed to be 0 up to 1,465 was classified. This model cannot give you anything good. But like the first one I shared with us, that is having just 1, 2, that was wrong, then it means most of the classification is going to be correct. It's going to be accurate. So before you start predicting using your model, you have to be sure all the metrics are perfect. You can't use this kind of metrics to predict anything. Look at it. Look at a matrix of 0.28. Look at the matrix of 0.19. Look at the matrix of 0.53. But 0.88 is still good. But all these ones, they are not a good one. They are not a good metric. So, and look at the loss. The loss is high. You understand? So before you begin to predict, before you begin to use your model, you must ensure you have all the. After that, that is when you are going to save your model. When you save the model, there is a way to call on the model. Depending, if I save the model, it's only going to be on my system. So if you give me, I can only predict on my system. So now for you to make it a global, something that can be used, maybe you now need, that is where other type of other people will now work with you. Maybe someone that can build an app. We now build an app, put that model in the app will now be using the model to predict. Or a web browser, put it in maybe in a website that immediately you just log in all those parameters. It's just like when you say, when you log in into some website and you put in something to just bring the outcome for you. Exactly. That is how the model will have been done. So the model will only be asking, if it's, for example, a web browser where you put it, the web browser will just be asking you, okay, what are the parameters we put in? So you are going to build it so that the browser will be able to ask for whether the individual is married or not. It is going to ask what is the balance in your account, how many days were you called, what was the duration, did you hear the campaign, how many times did you hear about the campaign, how many, I don't know what this understand. It's going to ask for this. I don't know what it means, except you go back and read what the description of the data. Were you called previously before this, and then what type of the job? Of course, it may not ask for the type of the job because you already have the listed job, so you just pick from them. And here, were you married or this and that? So you pick from it, married, divorced. Then level of education is going to be there. So you pick. As you are picking all those things, it's already putting it in the table, just like this. You are putting. Did you have a house by yourself, or did you have a loan? Did you do this? Were you contacted through phone or through mobile? You will fill all those things. Pick your age categories, then immediately you put that. Maybe you just pick evaluate. It's going to tell whether the individual will subscribe into it or not. So that is how to use the model. But it's not, the using of the model is the simplest thing. Is getting a good model that is important now. If you go and use a model that is going to give you a wrong classification, you may even give a cat to your model, and your model will be telling you that this is a goat. Because if all these metrics are not perfect, if you give a cat, you know this is a cat already, and you now give it to the model and say, model, please tell me what is this. The model will tell you this is a goat. Or might even tell you it's a lion. Of course, cat somehow resembles, they are both cats. Bigger cat and the large cat. It might be telling you it's a lion or tiger. It's going to be difficult when you have the same family, tiger, lion, leopard, cats, and like that. And you now give the common cat and it's telling you it's lion. So depending on the way you build your model. So deploying the model is not a problem. It's getting the model ready. That is how we work together as a team. If normally we are to work properly, the work of the data analyst with, okay, let's put it this way. The first person to work on this may be something like a data engineer that already have the data. They already have the data. They ensure you have a good data. So maybe from there, a data engineer can also help you to do some cleaning of the data, make it ready using SQL and stuff like that. We use a lot of SQL to work on it. After working on it, it now says, "Oh, you now tell you that now that you have your data, work on it." Okay, now say since I have my data, okay, where did you put it? I put it in database. No, okay, can I put it in Excel for you? Should I put it in a CSV file for you? Oh, please, I would prefer a CSV file. I will prefer an Excel file. So it's going to give you a prepared data. So if it's not putting it that way, it may put it in a database. That is where you are going to use SQL to just query it out. You are not using SQL for anything. It's just to query, or they may have a lot of data from in that particular what do you call it, database. You only query the only one you need. And when you query it, these are the only things you query: the age, the job. These are the only things you query from the database. That is the only place you need the SQL. After data analyst query it out, or it is given out by the data engineer that designed the database, then the data analyst will now say, okay, since I now have the data, okay, let me assist you as a data analyst before I give it to you to work on it as a data science. So as a data scientist. So the data analyst will now work on all these things, check, bin where it is supposed to be bin, do everything that's supposed to be done, and then at the end, give you a clean data. Then do some visualization for you. From the visualization, when it gives you the data, it gives you the presentation and says, oh, this data is containing some outliers. It's containing this, it's containing that. This is the distribution of the data. You as a data science, you now think of, okay, if it contains outliers, what can I do? Your work starts. You either remove the outliers or you correct the outliers. As a data scientist, you work on the data, you correct some of the imbalanced data and things like that. After you do that, you start the journey to build your model. That is why you are going to have enough time to build your model. Every other trouble has been done for you. So you can as well just start from this point of building a model from this point. Once the data has been given to you, cleaned and ready, the only thing that is left for you is just to divide the data into two, split your data into a training data, then begin to think about the models that you can use. Then you build your model. When you build your model, you check different models. You know, it's not going to be a big deal for you because every other thing has been done. You already have a ready-made data. Your own is just to split the data and then start working on it. Start working on your model. After you have worked on your model, you check your model, you check different metrics on it, and you try to turn your metrics to see that you have a good model. Once you are able to get a good model, say, for example, you get a model that is giving you 90-something, record 90-something, accuracy 90-something, F1 90-something. Oh, you now think you have a good model. Once you have your good model, you now say, okay, the model is ready. You save the model. This is the safe model. Take. So from that point, another set of people can start working on it. Because you as a data scientist, the model is only on your system. No hospital can use it on your system. If you have an hospital that maybe you build a model for them to check a cancerous cells or things like that, they can't use it on your system. It has to be on maybe on the web. It has to be somewhere as an app or somewhere for them to be able to access it, not on your system. That one may be beyond your capacity. The only thing you can do on your system is to save it on your system and test anything on your system. Well, you can do that. You test on your system, and that's all. You are the only one that can test on your system. But for it to be used, you cannot continue from that point. That is where other set of people will work with you. Maybe people that will build the app for it, people that will build the site for it, maybe web developers. Developers will work with you. So to ensure that the model is useful, or else the model will not be useful, the model will only be useful on your system. Except for some of us that, well, as for me, if I do the model, I don't need the model for anything. I only need it for publication. Maybe the next thing you see me now, I write a publication and set it to international journal. Oh, I've been able to build a model that is only on my system. And I have this I have this recall, I have this accuracy, I have this, and the public seat for me is going to be on my Google Scholar, be on this, be on that, and that's all. That is not a useful model. That is not, it's just for academic purpose. But if you want to build a useful model, after you have built your model, to put it into production, another set of people may have to work with you, except you have that skill. Imagine you are told now to build a site and put your model on the site, and maybe people can now begin to, it means you need another set of skill. That is not part of your job. Is another job entirely. So, but however, you can test it on your system. The easiest one to test are the things like an image. Image are easy. The only thing, you don't need any other thing. The only thing you need to is just to, for example, if I build a model that classify image as maybe male or female, I will just snap myself now, maybe through my webcam. I can just snap myself and upload it to the man. Say, model, check this. Is this male or female? The model will just tell you is a male or female. I don't need any other information. So for image, it's always easy to check image. But for non-image, you have to input all the features, which sometimes, well, you can formulate it. You just say, okay, if someone here where I have a balance, okay, let's assume someone's balance is 43. Let's assume someone day is 2. Let's assume someone duration is 35. Let's assume someone can pay is 1 or 0. Let's assume P days is 1. Let's assume previous is 1. Let's assume job is 2. Let's assume marriage is 0. Let's assume education is 5. Let's assume divorce is 1. Let's assume house history is 1. Let's assume loan is 1. You only assumed. When you assume like that, and then you feel it and say, okay, if you have this, what is it going to be? It's either going to tell you 0 or 1. We can do that. So that is where your work stopped. So, but for today, I have left so many things for us to go and practice by ourselves. In our next class, we may need to just test a model. Since we want to test, since we have something on our system, and I will try to see if I can build a good model that will give me good accuracy, good recall on my own. That is going to be out of the class. Then if I have the time, I will build that and then bring it to our last class next week. And then we try to check. We can just even copy anyone that we already even know the output from here. You can just copy anyone that we already know the output and use it to check. Or I build any smaller models that are easy to check. So we just check and see how we save our model. When we build the model, we save, and after saving, then. So please go and try so many things on how to tune your models. Thank you. I think our time has gone. So.
Hey guys.
Thank you very much. Thank you very much, Abdul.
Yeah, you're welcome.
Any questions for Abdul before we close out?
No more questions on my end.
No. Anybody else? Any questions? Lawrence, Olusola, Pauline, Adiega?
Not from my end. I'm actually working, so I just need to go and watch the video to get
Okay,
to
cool.
know. Yeah.
So next week is the last session. So if you think of anything that you want to asked Abdul from the previous weeks, then next week's probably going to be the best time to do it. If you want to DM me with the question, or you can put the question in the WhatsApp chat during the week, then Abdul can prepare the answer for you for next Saturday. And yeah, just real quickly, earlier on this morning, I shared with the early entrants that that we have a job board that is, well, we've had a job board for months where you can look at vacancies, but now we've got an actual CV database. So if you're looking for a role and you want to be seen by a lot of employers, now is the time to get your CV visible. The job board is being promoted directly to employers, in-house recruiters. So it'll take 2 minutes for you to upload your CV to get some availability. So I'll try and show you now. Here we go. So that's the landing page. Name, upload your photo, upload your CV, put a little profile in there as well. And then we'll get to work for you in terms of getting the visibility to employers that we have in our network. And typically these are inclusive companies who understand that there's that we need to increase the number of Black people working in tech, move it up from 2.5%. So anyway, any questions about that, let me know, or let Blaze know. And but if you're looking for a role, get the CV on there as soon as you can. And that's it. Have a wonderful weekend, and we will see you all next week. All right? Thanks a lot.
All right, thank you.
Thank you.
Yeah.